Hey, good morning, 7th grade. It's gonna be a little different today because I'm at camp and I believe Mr. Shrek is subbing for me. I'm gonna just give you my notes, give you a few demonstrations and talk about the 4 forces of flight, okay? I hope this all turns out well. I haven't done a video in a long time since COVID, so hopefully you can see the board and you can see the board there. In honor of Mr. Shrek, though, you know he's a Cougar fan, and you know we have the Apple Cup tomorrow. Let me start with a little joke, okay? There's these 2 Washington State University grads, and they're digging a ditch. That's kind of what they do. And they're digging along, and it's hot, and they're having a hard time, and they don't like it. And the one guy goes, you know what? We went to that fine university, Washington State University. Why are we stuck digging ditches? I'm going to go talk to the boss. So he goes up to the boss, he knocks on the door and opens the office, and his boss was a University of Washington grad. He's got, University of Washington gear all over the walls, and everything's Husky. And he walks in there, he goes, boss, I don't think I should be digging ditches. I went to Washington State University. And his boss goes, well, sorry about that, but Husky grads are just smarter. And the guy goes, no way! And his boss goes, yeah, let me prove it to you. So he holds his hand up to the cement wall, and he says, here, son, hit my hand. So the Wazoo grad winds up, tries to hit it, and the boss pulls his hand away, and the guy hits the cement wall. He's hurting his hand, and he's rubbing his hand, and the boss says, now get out of there and go back and dig a ditch. So the guy walks back, he trudges back, and his friend, of course, is waiting. He's like, what does he say? And the guy thinks for a second, he goes, aha, he said that you need to dig the rest of this ditch because I'm smarter than you. And the guy goes, no way, we both went to Wazoo. And the guy goes, yeah, let me show you. Okay, ready? Hit my hand. Anyway, we'll see what happens tomorrow. I believe the Huskies are going to do me proud. Okay, our topic for today is the 4 forces of flight. I like it because it's alliterative, 4 forces of flight, but also because it's going to teach you everything you need to know about not only planes, helicopters, the rockets you're going to build. We're going to make gliders next week. It's going to teach you about all those things. Okay? So, flight. There are 4 forces involved. By the way, I don't know if this is crooked on the, I can't see the camera. I don't know what's going on. Hopefully you can see this. There are 4 forces involved. In fact, maybe I should need to make this a little bit bigger. Is that better? All right. The first force that we're going to talk about is thrust. Little picture here of a rocket going up. Thrust has to do with one of Newton's laws, the 3rd law specifically. Thrust has to do with something is being thrown back, maybe air, maybe it's fire from the rocket, whatever it is, and that is creating an equal and opposite reaction. That's Newton's 3rd law. Now, I don't know how long to wait for you guys to take things down. You are very, very slow. So Mr. Shrek will just have to control this part, okay? He'll have to pause if it's taking you guys longer. So when the jet or the propeller or whatever it is it's throwing the air out the back, what that does is it propels the airplane forward. If it's a rocket, of course, you're throwing it down the bottom, it's propelling the rocket up. For you guys in your bottle rockets, we're going to put water inside of them and then fill them up with air. And then when we pull a pin, it is going to release all that water and air, throwing it out the bottom, throwing the rocket up in the air. So I just wrote down an example. Fire pushing out the bottom of the rocket pushes the rocket in the opposite direction so that it rises. The second force that we're going to talk about is gravity. Like a picture of these skydivers. We'll talk about this more in 8th grade when we do astronomy, but gravity is a force that is basically acting on everything near the Earth, because the Earth has this huge mass and it is pulling on everything. We would have to get very far away from the Earth and then in between other planets and things like that to really feel like there's no gravity. If you get close to the sun, the gravity of the sun is going to pull you in. By the way, that reminds me of another Wazoo joke. Did you hear there was this Wazoo professor and they were going to go study the sun? They built a rocket. They were going to blast off, land on the sun. And this reporter goes, "Sir, the sun is, millions of degrees. Aren't you going to burn up?" And the Wazoo professor goes, "Well, duh, we're going tonight." Anyway, so gravity is a force that when we're trying to fly, gravity is not going to be a very helpful force. It is going to try to pull you down. It's the reason why whenever I jump out that window over there, I don't flutter like a bird, I fall all the way down to the ground. Gravity is the attraction between two objects, and for us here on Earth, everything gets pulled toward the center of the Earth. There's a reason why if I take this pen and I drop it, it does not come stick to me, even though I do have gravity, but I don't have as much as the Earth. It gets pulled straight down to the Earth. Okay, I know you guys are still writing. Here's an example. If a plane stops in midair and the engine stops, gravity takes over and pulls the plane down until it crashes. Here's your third force, drag. Drag, like a picture of this runner. She's being pulled back by the parachute. Drag is also a force that is kind of hindering you from flying. You can think of some of these forces like some of them help you, some of them hurt you. Gravity definitely hurts from flying, and drag also hurts from flying. As something is moving forward, air molecules and particles bump into the plane or the rocket or whatever it is, and they slow it down. If I drew you two planes on the board, one like this, I don't know how to draw the rest of the plane, wings, and then a plane like this, and then a wing right there, and maybe the cockpit, pilot, you get the idea. Which plane's gonna fly better? Well, almost undoubtedly this one, because air is coming along and air might bounce into a little bit of it, but most of the air is just zooming right up. This one is gonna have air hitting it all along here, slowing it down. That's why we call this aerodynamic. Same thing that happens in the water with a submarine or a thing like that. We call that hydrodynamic, but it's the same thing. We want to create shapes so that the air does not slow it down, that it kind of slips off of it. Think about how a bird or a fish is shaped. They're usually shaped in these, ways so that they don't bump into the water, it kind of slides by them. Whoop. Oops, I don't want you to see all that. Lift lift is our last force we're going to talk about. Lift involves something, I think it's a really interesting and it's kind of a counterintuitive thing. So let me show you a couple examples. I hope you can see this. Think of this paper here. Now, if I blow under here, I can blow it up, right? What happens if I blow up here? Wouldn't you think that would blow it down more? But watch what actually happens. As I am blowing over the top of that, I'm increasing the velocity of the air, and that makes a pressure under here lift up the paper. That is called Bernoulli's principle. Let me show you another example of Bernoulli's principle. I have a funnel and a ping pong ball. Now, if I put this inside the funnel and I let go, what's going to happen? Genius. Yes, it's going to fall because of what force? Gravity. But, now, and also you would expect if I blow, that would just shoot it out of there faster, correct? But remember what we just talked about with Bernoulli's principle. If something is moving faster, like me blowing over the top of that paper, it creates a force underneath of that. So watch. It's only when I run out of air that it actually falls. Now, I'm not sucking in. I don't have that much air. I can't, or that big of lungs. I can't do that. I'm blowing out. And as I'm blowing out, I am creating faster air above, slower air below, and that pushes the ping pong ball up, almost like a giant hand. When I do that for a wing, wings are shaped, kind of what happened is they watched birds and they looked at the shapes of their wings. As the air comes in here, it ends up going faster above than it does below. And because it is faster here and slower here, you get an area of high pressure here and low pressure there. If you have high pressure below, that is going to push up. That is what we call lift. Write that down. It's Bernoulli's principle. Air moving faster has less pressure than slower moving air. And so with wings, they're shaped so that the air moves faster over the top than on the bottom. So there's a higher pressure below, which ends up pushing up.
It's often said that lift on a wing is generated because the flow moving over the top surface has a longer distance to travel and therefore needs to go faster. This common explanation is actually wrong. This video shows that the air on the top does move faster, but it doesn't reach the end of the wing at the same time as the air along the bottom. Here we use smoke to visualize the streamlines around an airfoil. We can pause the smoke by briefly interrupting the supply. This gives us lines that travel through the flow, as we can see here. And if we now slow the video down, you can follow those lines, and that gives you an idea of how fast the flow is in different parts of the airflow. Here you can see it speed up as it approaches the airfoil, and it moves faster over the top compared to the bottom. You can see that it reaches the end on the upper surface much earlier than it does on the lower surface. In fact, by the time it reaches the end on the lower surface, the flow has already gone a long way past on the upper surface. This shows very clearly that the flow doesn't take the same amount of time to reach the end of the wing.
So those are the four forces. You have thrust, You've got drag, you've got gravity, and you've got lift. Two of them are pretty helpful in flying. In fact, I don't think you can fly without thrust and lift. Two of them hurt you, gravity and drag. Now, I might ask you on the test, I might ask you different questions like, okay, let's say we go to space. What's going to happen to the four forces? Well, think about it. In space, there's not going to be any drag because you're not hitting any air molecules. There's not going to be any gravity if you get far enough away from the Earth. There's not going to be any lift because there's no air moving below and above your wings. So the only thing there's really going to be is thrust. You can still, even in space, you can use Newton's third law. You can throw something out the back, forcing your craft forward. Okay, so there's an example. There might be other examples I give you. I might ask you, what would be the problem with having a really large aircraft? A large aircraft, think about it. A large one is going to have a lot of space for air to hit it, so that's going to be a lot of drag. And also larger, usually at least, implies heavier, so that's going to have more gravity. Anyway, just a couple examples. I'm going to give you a short worksheet due the next time that I see you, and that's just a chance for you to apply these four forces to real life situations, okay? It's short, easy, don't sweat it, don't cry, stop crying. Got a couple of videos for you first. First video I'm going to show you is this awesome paper airplane at a soccer game. Watch it.
3, 2, 1.
Oh, what a shot. He brought the place to its feet.
You're absolutely right.
But Andy, there's the fullback. Oh, what a shot. He brought the place to its feet.
You're absolutely right.
Isn't that amazing? I like that you can see it from above, but then you can see it from the TV view too, and you see it hit the player. And here's a short little video just summing up the four forces of flight. I'm going to include this.
In the air because of one simple fact. There is no net force on them. And with no net force, an object at rest stays at rest, and an object in motion stays that way, even if it's in midair 10 kilometers above the Earth's surface. Now, of course, it's not like there aren't forces acting on the airplane. Gravity pulls down on the plane itself, plus all of the people and baggage inside, and every single air molecule that's shot through the engines or collides with the fuselage or wings pushes on the plane as well. But if all of these forces are balanced, in particular if the air molecules push the plane up enough to counteract gravity, then the plane stays up. Getting air molecules to push the plane up is the crucial part of flying, and planes do this by making sure the undersides of the wings crash into more air molecules more violently than the upper sides. When a plane is parked on the ground, air molecules bounce off of the top and bottom of the wings in roughly equal amounts, or with equal pressure, and no lift. But in motion, the curved shape of the wings and their slightly inclined angle means that the bottoms smash into more air molecules than before, and smash harder into those molecules, so the pressure on the bottom of the wing goes up. In addition, fewer air molecules now strike the top of the wing, and those that do strike it less forcefully, partly because it's being shielded by its own forward motion, the way running into the rain keeps your back drier, and partly because a curving stream of air has lower pressure on the inside of the curve since the molecules get thrown centripetally to the outside. But whatever the reasons, the pressure on the top of the wing goes down. So low pressure or less downward force on the top, plus high pressure or more upward force on the bottom, and the plane has lift. And if the force imbalance is big enough, it can lift the plane up into the air against gravity. Now, all this crashing into air molecules to lift the plane also pushes to slow the plane down, which it would if not for engines. Engines also push air, in this case backwards, either via a propeller or a jet driving a propeller. For various reasons, it turns out that you want to have a really big propeller driven by a really small jet, for the most efficient engine. But even in inefficient engines, the spinning fan blades generate their thrust, which is essentially horizontal lift, by moving quickly through the air with a curved shape and a slightly inclined angle. They're essentially mini wings. And so an airplane is essentially a meta-wing. It flies by moving mini wings fast enough to push air molecules backwards, which moves the plane forwards fast enough that its big wings push air molecules down. Whoa. Wingception.
I'm just going to insert a couple more videos here. Here's a video of a guy, a cyclist, who figures out a way to really cut down on his drag, okay? I might try this next SDP. Of my son skydiving. He has a skydiving license and he likes jumping out of planes. Here's how he had to get certified. And so he's jumping with somebody else and they're telling him to do certain things. You know, go away from me, come back, roll over, do all these things. Here's this little video. And here's a short little video of a guy using one of those wingsuits. And incredibly dangerous. I don't know why you would do this, but he's going through this keyhole in this rock formation, and it's pretty incredible.
Se sia cosa sarà 2 metri, 2 metri e mezzo, 2 metri 60, 70, non so.
Dopo lo spianto di ieri, ci riprovo, questa volta dall'altra parte sto salendo, questo è
lastly, here are some incredible flying machines. Hopefully your rockets and gliders are going to look better than these, but I just thought I would include this just because they're so amazingly terrible. Okay. Okay, guys, have a great weekend, and I will see you next week, okay? Bye-bye.